Hello, welcome back to the first course in general physics. So far, we have been discussing mechanics of particles and mechanics of objects. We have been dealing with the description of their forces, of their motions, the relations between the motion and the force and the energies, kinetic energy, potential energy, and mechanical work were involved in our previous study. And that is simply the field of mechanics and the consideration of mechanical energy. Now we move to a different topic, to another field of study, the field of thermodynamics. In this field, the systems interact with their environments, with other systems, and exchange heat, which is another form of energy, not mechanical energy, in addition to exchanging mechanical energy. So this is another field of study that we move starting with this lecture. So this will be the first lecture of thermodynamics. And in this series of lectures to come, we will be discussing the following topics which are relevant to this field of study. We will talk about temperature, this central concept, and we will arrive at the zeroth law of thermodynamics. We will define the temperature, see how it is calibrated, and what it means, what is its significance in thermodynamics, and then discuss the zeroth law of thermodynamics, which did not come until very recently, a long time after the first law and second law have been stated. And after that, we will talk about the thermodynamic systems. We will discuss thermodynamic systems and define these systems. We will discuss the relation between the temperature and heat. We will talk about thermal equilibrium, heat capacity and specific heat, and heat of transformation in this context. We then move to another topic, which is the relation between heat and work and mechanical work. Finally, after discussing the concepts of heat and work, we will arrive at the first law of thermodynamics. We will discuss few special cases of this law. After that, we will be discussing thermodynamic processes and how to analyze these processes and evaluate the energy changes, exchanges, and transfers, and so on. Then we will take the ideal gas case as a system of study. The ideal gas case, in the ideal gas case, we will study the ideal gas equation. We will discuss the isothermal expansion of an ideal gas. We will also state the internal energy and on what parameters does it depend. We will talk about the molar specific heats of an ideal monatomic gas. And then we will tackle the problem of the adiabatic expansion of an ideal gas. Finally, we will talk about the free expansion problem of an ideal gas. After we have finished the discussion of these issues relevant to the ideal gas behavior and thermodynamics of ideal gas, kinetic theory of ideal gas, we will move to another field of study in the context of thermodynamics, and we will talk about the entropy, a new concept, a new physical quantity, and we will be deriving or stating the second law of thermodynamics and its consequences. And then after that, we will talk about some applications in real world heat engines or thermal engines. In that context, we will discuss the Carnot engine, an ideal engine, and we will have some applications, some real engines to talk about. And then finally, we will talk about refrigerators and heat pumps and air conditioners and so on. These will be the topics that we will be discussing in this subject of thermodynamics of systems. At the beginning, we would like to remind ourselves that thermodynamics, as we said, is the field of study of systems which are not closed systems like the systems we have encountered when we discussed the concept of conservation of energy for systems, for mechanical systems. This is an extension where we consider systems interacting with their environment and exchanging heat as well as work. Thermal energy, which is a type of an internal energy, is involved in this process, in this subject, in the discussion of the field of thermodynamics. But before we go on, we would like to introduce a concept that is very relevant to the study of thermodynamics. This concept is a well-known concept in our everyday life, which is temperature. Temperature is a central concept in thermodynamics. What is temperature? To us, it's the feeling of how hot or how cold is an object. How do we measure the temperature of an object? One way could be just to touch it to see how hot it is or how cold it is. Touching two objects might give us an idea about which object is hotter than the other. However, this method of dependence on our senses to measure or describe the temperature or how hot is an object is not really reliable for one good reason. Because what we sense is the relative temperature of the object relative to our skin where we touch that object. So for example, if we are very cold, if we come from outside where it's very cold and we feel very cold, our fingers are very cold, then even a moderately cold or warm water will feel hot, and vice versa. If we feel hot, the same water could feel cold, seem cold to us. So sensation is not an accurate method for measuring the temperature. We cannot depend on our senses in that sense. So what do? We have to set a scale for measuring the temperature so that the numbers have meanings, because as we said in the introduction of this course, the quantities have to be described accurately by numbers. That's how we arrive at an accurate description and an accurate conclusions about the properties of the systems we are studying. Temperature is thus agreed upon internationally to be one of the 7 base quantities in the international system, and it must have a scale of numbers, and the scale that scientists use to measure temperature is the so-called Kelvin scale, and the unit in the SI system is capital K, that goes for Kelvin. Of course, there are other units that are related to the Kelvin scale, but this is the scale in the international system. How do we measure the temperature of a system? How do we set the scale for measuring the temperature? We notice from our experience that the properties of many objects or materials change as their temperature changes. For example, the volume of a fluid increases as the temperature of the fluid increases. The length of a metal rod increases a bit as the temperature of the metal rod increases. The electrical resistance of a wire increases as the wire gets hotter. And other relevant or irrelevant properties of matter change with temperature, with changing the temperature of the object or of the material. Now, we can depend on one of these properties as the basis for measuring temperature. For example, we can depend on the volume of the fluid as it changes with increasing temperature to measure the temperature. We can enclose some fluid in a container that is attached to a very thin pipe, and we can use a known point, for example, the freezing point of water, and at that temperature where the surface of the fluid in the pipe comes, we can put a mark and call it the freezing temperature of water. We can start increasing the temperature of water until it boils, for example, and we put another mark and we call it the boiling point of water. Then we have two marks between the freezing point and the boiling point of water, and this distance between these 2 points, between these 2 marks, we can divide it or subdivide it into the divisions and make the scale that is comfortable for us. That's how we use, for example, the volume of, or the increase of the volume of the fluid as a measure or a basis for measuring the temperature. The resistance of a wire also can be used as the basis for measuring the temperature. What are the limits of temperature? Does temperature have limits? Indeed, temperature has a lower limit. But in principle, temperature does not have a higher limit. You can go as hot as you can in terms of temperature. The lower limit is defined as the 0 on the Kelvin scale. The higher limit is open. It can be very hot. Millions of degrees is still cold enough. Since, for example, at the beginning of the creation of the universe from the Big Bang, right at the beginning, that spot at the Big Bang point was 10 to the 39 Kelvin hot. And that is a very, very hot temperature. That was the temperature of the universe then, when it was a point. Now, after the universe has expanded and cooled down, the average temperature in the universe is 3 Kelvin, which is very cold, very close to zero, 3 Kelvin. That is lower than the liquefaction point of liquid helium. However, we are at about 293 Kelvin. 293 is about 290 degrees Kelvin above the average temperature in the universe. And that is because we happen to be living near a star, a very hot star, which is the sun. If we did not have that sun around us, and if we were living in an average temperature, like the average temperature in space in the universe, we will not be existing, because everything almost solidifies at 3 degrees Kelvin. It's a very cold temperature, and it's impossible for life. So that's how cold and how hot objects can be. But when we talk about the scale for measuring the temperature, the reading that we get should have a physical significance. Since any scale, a thermoscope, for example, can give us an idea about the relative temperature of one object with respect to another object. That is, it can tell us whether object A is hotter than object B or colder. That's a thermoscope, where it just gives numbers as indicators. But in order to convert numbers into a physically meaning quantity, we have to calibrate the scale. For example, to say that this point on the scale is the boiling point of water, and that point, for example, is the freezing point of water, and so on. That's the calibration. Now we talk about the interaction between two bodies. Suppose that two bodies are in intimate contact with each other. If one of these two bodies is hotter than the other, then heat will flow from the hotter object to the colder object. But if these two objects are at the same temperature, that means if they are at equilibrium, at thermal equilibrium, then there is no heat transfer between the two. Now, the zeroth law of thermodynamics states that if we have two objects, two bodies, A and B, if these two bodies are in thermal equilibrium with a third body, T, then they are in thermal equilibrium with each other. That is, if A is in thermal equilibrium with T and B is in thermal equilibrium with T, then we conclude from the zeroth law of thermodynamics that A and B themselves must be in thermal equilibrium with each other, without having to do the experiment of really getting them into intimate contact with each other to check whether they are in thermal equilibrium or not. And this law was given the number 0 because it came very much later than the first law and second law, after they have been described and stated and given the numbers. But since it is very essential, and the temperature as a concept is very essential in the study of thermodynamics, this law was to be given a number that precedes, that comes before the first two laws, and thus the number 0 was given. We did not have any alternative. This law, the 0th law of thermodynamics, is a useful one where we use it in our laboratory so often. For example, if we want to check whether two bodies have the same temperature or not, we have the two bodies, and then we bring a third body, which is the thermometer. A thermometer is a calibrated thermoscope. That means the numbers have meanings. And we get the thermometer, which is the body T, the third body T, we get it into intimate contact with body A, and we read the scale, that's the temperature of body A, and then we put it into thermal contact with body B, and we read the scale on the thermometer. If the scale on the thermometer reads the same in both cases, that means body A is in thermal equilibrium at this scale with T. At the same scale, body B is at thermal equilibrium with T. That means A and B must be in thermal equilibrium, which means A and B must have the same temperature. And that is indeed what the scale gives us, the same temperature. This is the 0th law of thermodynamics. Now, we move to the definition of a thermodynamic system. What is a thermodynamic system? A thermodynamic system is a system that interacts with the surroundings, with the environment, and exchanges heat with the surroundings in ways, one of which is the exchange of heat. So, the thermodynamic system is a system which interacts with other bodies around and exchanges energy in forms that are either work, which is the mechanical, which has been encountered before in the context of the mechanics of bodies, and it also can exchange energy with the surrounding in another form, which is heat. That form of energy exchange was not encountered previously in the discussion of mechanical energy. And what is now the connection between these two concepts, temperature and heat as energy? The temperature of a system T sub S, if the system gets into contact with the environment, with another body or with the system of bodies in the environment, if the system's temperature T sub S is different than the temperature of the environment T sub E, then the system, as we mentioned, will exchange heat with the environment. Thus, heat exchange occurs only when the temperature of the system is different than the temperature of the environment it is in contact with. Thus, if the temperature Ts is different than Te, Ts will change. The temperature of our system will change. Until when does it change? Heat will keep flowing from the object or to the object until the two temperatures, Ts and Te, are equal, in which case we reach thermodynamic equilibrium or thermal equilibrium. At that point, when Ts is equal to Te, then no heat will be transferred to or from the system, and we are in thermal equilibrium. This slide shows an example of the interaction of a system with the environment, where in the upper case we have the system has a temperature higher than the environment temperature. Ts is greater than T sub E. In this case, through the interaction of the system with the environment, the system will lose heat. Heat or energy in the form of heat will be transferred from the system to the environment. And in this case, we say the heat Q is negative. Thus, we measure the heat Q as the thermal or internal energy of the system as being positive if the system gains heat. And if it loses heat, the heat Q is negative. So in this case, when Ts is greater than Te, Q is negative, and the system will lose heat to the environment. In case B, we have the system and the environment at the same temperature. In this case, we are in thermal equilibrium. We have thermal equilibrium between the system and the environment, and heat does not exchange or does not transfer to or from the body. There is no heat, and thus Q is equal to 0. In the last case, we have the temperature of the system smaller than the temperature of the environment. So the system is colder than the environment, and thus heat flows from the environment to the system. And thus we say that Q is positive in this case. Thus, through the interaction of a system with the environment, the system exchanges heat as a form of energy, thermal or internal energy, with the environment, and this heat exchange in terms of heat flow, it can be either positive in the case where the system is colder than the environment and heat flows into it, or it can be negative if the system is hotter than the environment and heat flows out of the system. So these are consequences of the interaction between the system and the environment. Now, the heat is some form of energy, thermal energy. However, this energy is different from other properties of the system, such as its pressure or its temperature or its volume. It is different than those properties in the sense that the heat Q is not an intrinsic property of the system. it is not measured in terms of the state of the system. So the volume, for example, or the pressure of the system or the temperature of the system is a measure of the state of the system, depends on the state of the system. However, the heat is not a quantity that is a function of the state properties of the system. Thus, we don't say, for example, a system in a given state has that much heat as energy. We don't say that. We can say that the system has that much as potential energy, for example. But we cannot say it has that much as heat or as work, for that matter. So even work, also mechanical work, is similar. It is measured in terms of how much energy is transferred to the system or transferred from the system. But it's not measured in terms of the state parameters, which are temperature or pressure or volume or whatever. It's not measured in terms of the state parameters of the system. The units of heat traditionally were taken as the unit of heat was taken as the calorie. And the calorie was defined with respect to heating water. So the calorie is defined as the amount of heat required to raise the temperature of 1 gram of water from 14.4 degrees centigrade to 15.5 degrees centigrade. That is 1 degree centigrade, between 14.5 and 15.5. The heat required to raise the temperature of 1 gram of water 1 degree centigrade between 14.5 and 15.5 degrees centigrade is the unit of heat, calorie. The degree centigrade, which is another measure of the temperature, is the same as the degree Kelvin. It's exactly the same. They are different, the Kelvin scale and the centigrade scale, they are different in their reference point, where is the zero of each scale. They differ in that sense, but they don't differ in the degree itself, in the amount of degree itself. So we can say, again, the calorie is also the heat required to raise 1 gram of water 1 degree Kelvin between this temperature and that temperature. There is the British thermal unit. We don't use the British system of units. We use usually the international system of units, but so far those are the traditional units that we are encountering. They are not the international system of units of heat. And the British thermal unit is defined as the heat required to raise the temperature of 1 pound of water from 63 degrees Fahrenheit to 64 degrees Fahrenheit. That is another traditional method or unit of measuring heat. However, based on the fact that heat is energy, there is equivalence between heat and energy. Heat is some sort of a thermal energy or internal energy. Thus, the international system of units is adopted to define the unit of heat, and the unit joule, which is the same unit as energy for energy, was adopted in 1948 for the first time, and thus the joule is the unit of heat in the international system of units. And that way, the calorie, the traditional unit of heat is measured with reference to heating water, in terms of heating water. However, the international system, the joule, the unit in the international system, is measured with no reference to heating water, and the equivalence between the two units, actually between the three units, between the international system of units and the two previous units, is as follows. 1 calorie is equal to 4.186 joule, and that is equal to 3.969 times 10 to the minus 3 British thermal units. This is the relation between the joule, the unit of heat or energy in the international system, and the traditional units of heat in the that were used in the past. And now we define the heat capacity. What is the heat capacity of an object? The heat capacity C of an object is defined in terms of the heat absorbed by the object at a given temperature when it interacts with the environment, and as it changes its temperature from T initial to T final. That amount of heat is given by Q is equal to C, capital C, which is the heat capacity of the object, times the difference in the temperature achieved due to the absorption of the heat quantity Q, Tf minus Ti. So Q is equal to C times delta T, Tf minus Ti. And when we say Q absorbed, it could be, as we mentioned, positive or negative. That means if the final temperature of the object is higher than the initial temperature, then Q is positive, and we say that the object absorbed heat, positive heat from the environment, and vice versa. If the final temperature is lower than the initial temperature, then delta T is negative, and we say that the system absorbed negative heat, or it lost heat to the environment of the amount Q. At this point, I would like to finish this lecture, and I thank you for your attention.